Recording now. Over to you.
Thanks, Bill. Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials, and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve, and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. For the most effective results, Happy has advocated selecting your own engineers who are already familiar with your own processes and procedures and letting them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Having begun the series with an introduction to the elements of automation and the journey to your smart factory, Happy identified the key issues: who, what, how long, when, and how much. Since then, he has discussed a series of skills, including total quality control, Six Sigma and statistical tools, problem solving, design of experiments and predictive analysis, benchmarking, product and process life cycles, engineering economics and road mapping. He defined automation and automation methodology and examined the realities of the smart factory, then looked in detail at sensors and chemical analysis. Last week, he focused on figure of merit, metrics and dimensional analysis, and lean manufacturing. If you missed any of these earlier sessions, they have all been recorded and will be made available to you. And if you have any specific questions, please direct them to happy@iconnect007.com. In today's presentation, the 8th in the series, Happy explores a further 3 essential skills: quality functional deployment and house of quality, predictive engineering, and online instruction and distance learning. So with our sincere thanks for so generously sharing his knowledge and putting together such a splendid series of presentations, it gives me great pleasure to hand over to Happy Holden.
Thank you, Pete. Oh, shoot. I gotta click on this thing, but there we go. There we go. Hopefully you can see my screen all right. Thank you, Pete, for another great introduction. This is my last one of this series, but fortunately, we have a surprise for you for another expert that's come forward. And so maybe we'll look forward to more of them. Today, we'll go over my last three that I selected: quality, functional deployment, predictive engineering, and distance learning. The last three out of the many. Again, these are chapters in the 24 essential skills. I'm only going to spend 15 or so minutes on them, more detailed in the book. And the book only introduces the subject. This quality functional deployment, we call QFD, it is a strange name. It's actually, the English name comes from the translation of the three Japanese symbols that make up. So it's actually, quality, separate, functional, separate, deployment, a little bit obscure, and in many ways a very complex methodology the Japanese have developed on product strategy. The first house of which is called the house of quality, but then more about the deployment and how we use it in printed circuit fabrication to create our roadmap and investment in future technology. But it's a very interesting thing. I actually spent 5 days in Detroit at the Automotive Supplier Institute, learning this technology in much more detail. Again, developed in Japan, primarily from Toyota and others. It was quickly adopted by Ford and used very effectively in producing some of their more popular models. It's also called the House of Quality in that it's really quite an involved analytical process. But in my 50 years, this is the most effective way of translating customer needs or strategic direction or strategic imperatives that companies may have into product processes or performance objectives or programs in terms of some type of a roadmap, and then defining the technology infrastructures and technology advances needed to do that technology roadmap that then creates action plans and investment strategies. Many times moving between these different stages is a lot of arm waving and opinions and everything like that. This House of Quality, QFD, is the best analytical, based on data, and not necessarily an opinion, of translating needs and directions into action plans and strategic investments. One of the things from the original Harvard Business Review article in May of 1988 was the focus that Japanese automakers with QFD made fewer changes than US companies without QFD. And that's because the QFD provided a much more thorough focus on needs and objectives than typical US companies had in the past. And the same way that Japanese companies improved the invention of DFMA that US came up with, but having been improved by the Japanese and then coming back, you see a much improved system once we learned how the Japanese did this. You notice that this first comes from a Harvard Business Review article in 1988. And so, in the 80s is when, I went to school and learned of this technique thoroughly. And it's called the House of Quality, basically because some of the diagrams look like houses. There are five key points to QFD. Understanding customer requirements, but also strategic directions or company prerogatives and focuses based on quality system thinking and knowledge, and I'm not sure what epistemology is. Maximizing positive quality that adds value, a comprehensive quality system for customer satisfaction, and strategies to stay ahead of the game. It consists of 4 main steps: identifying customers' vital requirements for the product or services and translate them into design requirements, and developing a service blueprint, an effective and efficient delivery process, evaluating the alternate designs or processes, and then implementing the newly designed processes for delivery of products and services. And you can see here the rooms in the House of Quality basically start with the thing how. And so there are design requirements and customer requirements, and a correlation matrix, relationship matrix, importance, customers rating, and customer competitive assessment, and then objective values, how much, and then technical competitive benchmark, engineering assessment, and importance. So this relationship matrix is, what do customers need? But it's not always that. It could be, what are the strategic roadmap imperatives? What are the business objectives for our company? And then how important is each need to the success of customer satisfaction and business progress, and sensitivity analysis? And then how do customers perceive you and the competitors? Choice modeling there. And then what targets should we set for product specification involved in each relationship? Again, a lot of this is using a car example. And in fact, some of the actual QFD matrix employed, you can see here in terms of actual diagrams. Interesting enough, these QFD houses now are available electronically. I'll show you towards the end. And as this has been turned into software that's easy to download. But, you can see the customer requirements translating into design requirements in terms of strong and negative interactions, high and low performance. This part of the original article in May of 1988, relating to automobiles, our car, in looking at comparing what they were designing as well as competitive cars A and competitive cars B, as well as details in terms of technical data and technical difficulty, importance, estimated costs, and different areas of the relationship. The QFD roadmap really starts with the scope of the project. What are the risk and return? That's one reason that we not only used it for product and process design, but also for investment in terms of automation and new technology acquisition, and or new materials or other elements. Identifying customers, images, and voices. What does the customer need? Or you could also add, what does the company need to fulfill its goal of higher quality, higher profits, more diversified delivery performance? And then QFD number 1, determining the functional requirements. What are the measures for the needs, taking from needs to measures of performance? And then creating and selecting concepts. What are the best concepts to meet these needs? And then QFD number 2, determine design specifications. What are the offering characteristics in terms of design? And selecting the process. how do we make it? Reading to QFT3, determining the process specifications. What are the control values and process specifications to define the control methodology? So there are what we call linked houses that convey this needs through to manufacturing and or production planning, from the house of quality, where we have customer attributes, to deployment, where we have engineering characteristics, to process planning, which are parts characteristics and key process operations, to production planning. And you can see that this can easily be used as the methodology of how do we implement automation for our business objectives for the next few years, in terms of which are the most competitive, the biggest bang for the buck, and how difficult it's going to be and resources required. So the linked houses of quality all the way through thing are one of the reasons why we use this so much in Hewlett-Packard was that Hewlett-Packard, towards the middle of my career, had 21,000 different electronic products. And, like I said, they were getting to about $20 billion a year, with 54 autonomous divisions making computers, test, medical, nuclear instrumentation, and moving into the area of biological and genetic test equipment as well, that we were desperately in need of a really factual and understandable methodology to translate what the technology and the customers were telling us down into actual products and processes that we may need. So from these customer needs to process performance requirements to process design specifications to process control specifications wasn't important with that. You can see that first house of quality, the methodology identifies critical process implementation specifications of the selected concepts. So you define and prioritize customer needs and or company needs for the future, analyzing competitive opportunities, plan to respond to the needs and opportunities, and establishing critical characteristic target values. And then moving on with the output, which are the engineering characteristics, into identifying critical parts and assemblies, flow down critical product characteristics, translated into critical assembly characteristic and target values. This then flowing into process planning, determine critical processes and process flows that may be improved or acquired, develop production equipment requirements, and establish critical process parameters, which would flow down into determining critical parts characteristics, establishing process control methods and parameters, and establishing inspection and test requirements. In the commercial field, not available when we started, but available now, are ones like this, which is a company you can find on the internet that provides training instructions. Some of their overview of QFD, you can see here. Again, they had the multiple houses, starting with the house of quality in needs and directions. And then, is this evolutionary or revolutionary into the functional mapping of these objectives, into design deployment, and then into process planning, and eventually, through production control. And so, these companies available, to provide that steps in developing product and services, but also, like I said, it can be used in our case of investment in projects. You're going to find, if you look at QFD, different views of the house of quality in terms of 3 different ones I've referenced here from 1986, 1988, and again, the original one from the Harvard Business Review in terms of how they've taken the Japanese things and morphed it in different ways for different reasons that different companies have. Like I say, as far as I know, QFD from the Japanese point of view is not copyrighted or anything like that. So it's open to manipulation of its strong points and ignoring other parts that may not be useful. Now, we use this a lot in printed circuits. Being a captive printed circuit and flex manufacturer for going on to a $20 billion company, these 64 divisions were going in every different direction possible, from massive business computers on one side and their software, low-cost printers and peripherals on another one, but super sensitive test equipment, and even moving into optical equipment in which we had to deal with 100 to 200 gigahertz signals because we're moving back and forth between photonics and optical communication and electronics test equipment for those. And then moving into the whole genetic engineering, which is another talk if you want to talk about the future, because of the involvement of biological and bacterial elements as part of an electronic system that we got involved with. So we had a lot of conflicting different customer needs that we would segment down into what we call an egg chart for our products into different segments of the market, and looking at competitive analysis of what competitors had in terms of materials or technology, and then being mindful of our customers typically had a vintage chart of their roadmap that they planned for the future, what we had, so that we didn't end up with, a packaging system for our different segments of the market that we were supporting. And this is where QFD came in, because we took customer product needs and determined them into customers' packaging substrate attributes, their wants. And then, planning this with other inputs from councils and competitive analysis data into design requirements that they would going to bring and performance targets into the PCB part deployment in terms of product planning, which then would lead to a PCB characteristics and a technology R&D roadmap that we'd have to work with. And from the roadmap and QFD into the process planning of necessary processes and performance, eventually then into production planning for equipment, investments, expansion, and looking at our production requirements in terms of CPK, yield analysis of current and future manufacturing capabilities, and then gap analysis and some obstacles to implementation. This would eventually lead to project objectives and deliverables that were then formalized into specific programs and projects that we would have to work on with our staff. Here's another one, not necessarily, but as we talked with other companies using QFD, this is one of their ones, and you can see that in QFD1 and QFD2 in terms of planning, the roadmap in terms of this 15-step process using QFD twice. In fact, here's part of HP's product definition effort that you'll find in another chapter on a product life cycle, but this one indicates, again, the use of QFD in specific steps in the product definition and in terms of product positioning and benefits to customers that HP would use. And so QFD is it can be a confusing and complex methodology, and it's not one you hear about now since it started in the 80s and 90s, mainly because a lot of companies have institutionalized it and don't talk about it, so you haven't heard it. But I still can say that it's the best one out there. It's one of these essential skills that you can read up on it after my book by going to the internet and look to see if this is going to be a tool that'll help you move along with your programs. Which brings me to the second area today, which is predictive engineering. And so predictive engineering came about because my definition of design for manufacturing assembly, DFMA, was defined by two university professors, Dewhurst and Boothroyd, as a predictive methodology of how you design a product right the first time. DFM is not design rule checking. In other words, finding mistakes in your design. The basic definition of DFMA is one of methodologies and data and simulation that allow you to design the optimal product the first time and not have to do respins. And because DFM now has so much of a industry focus of testing and rework and redesign, I started using the term predictive engineering because DFMA, nobody was buying into our definition of it. These trade-offs on design cover 6 key topics: optimization of grids and layouts, minimization of PCB substrate costs, minimization of assembly costs, use of preferred parts, analysis of test coverage, and partitioning of ASIC pinouts. So one of the goals of the smart factory and digital twin, in many ways, is the improvements of these DFA tools that help designers in the first place do placement, routing, output, prototype production, and volume production. And in many ways, the smart factory and the digital twin hopefully will provide advanced DFX tools on signal quality analysis and HDI analysis, everything else. So the opportunities for predictive engineering in electronics is that products have become increasingly complex. Not only the product has to meet expectations of customers, they need to be environmentally friendly, energy efficient, conservation of resources, and even obsolescence and destruction. And all of this done in an ever-shrinking product life cycle. So minimizing costs is imperative. So DFMA benchmark shown in cases studied to reduce assembly costs by 35% and pure circuit board costs by 25%. 75% of the manufacturing cost of a product is determined by all the design drawings and specifications. So in the electronic product design process, 60% of the manufacturing costs are determined in the first stages of design when only 35% of the design cost has been expended. The product definition process includes specification and partitioning. This is the technology trade-off analysis where you balance the loss and gain in various domain performance versus cost. And so in many ways, a common language has to be established to link manufacturing to design and R&D. This common language defines producibility as an intrinsic characteristic of design. So we talked about last week, figure of merit, which was very important to get a common definition of producibility that was actually an algorithm and an equation that not just could manufacturing calculate producibility from a design, but the designers themselves could calculate producibility. And if it didn't meet a minimum level of producibility, they knew it's not time to throw it over the wall. They'd go back and figure out and ask for help in production of how to get this to a design level. So the nature of the problem that we have in the industry is that, design goes and produces things into manufacturing. But design and manufacturing work on totally different timetables and things like that. The element is, how do you get a feedback in terms of there's no provision for the capabilities, experience, and wisdom gained in manufacturing to flow back into the design environment. So one of the methodologies we did while I was in charge of design was that you have the layout, which everybody established, but we spent a lot more time upfront on the planning in terms of wiring predictions from the bill of material and data to look at what we call wiring demand, and then looking at design rules, schematics, signal integrity rules, and our architecture, a thing called routability predictor and layout efficiency. If you've never heard of routability predictor, don't know what it is, and if you've never heard of layout efficiency as well as wiring demand, then you realize that you don't know and understand the physical, mathematical measures of performance in printed circuit design. And if you don't know the measures of performance, then anything is possible, including junk and things that cannot be built. And like I said, when you take all of this and you come up with the estimated first pass yield that we talked about last week, the digital twin model can predict first pass manufacturing yield plus or minus 3%. And this essentially then drives the layout in terms of doing this right the first time and not having to go back and do it over respins. And so predictive engineering talks about this concurrent manufacturing framework of CAD seats and bill of material and the machine programs, package and parts information. But to find a home for this, I call that the mechanical, electrical engineering, signal integrity, power integrity, reliability, the concurrent engineering that goes on in design. But instead of coupling directly into concurrent manufacturing, there has to be an intermediate area that manages the time differential, which we'll call product data management. But these product data management systems, databases, is the home for a product the rest of its life, including obsolescence. And with concurrent engineering, working with the product data management back and forth, then concurrent manufacturing can produce the prototypes and the what ifs and provide advice, but not necessarily back to the design people, being caught historically in the product data management to cover the entire design life cycle. And this is where then Industry 4.0 needs to deliver the predictive engineering framework using data from past designs in manufacturing and field performance to provide the planning and trade-off tools for new designs in concurrent engineering, as is seen here. So, this is a inherent part of Industry 4.0 in the focus of data and prediction from that data. One of the software tools that I have, is this software that I put together in over 30 years, which consists of 50 separate Excel models, all tied together with Excel macros, providing a simulated prototype. In other words, we could, from a software, actually create a prototype board, test its performance and its cost and reliability before we ever opened up the CAD system. And this allowed us then to look at improvements and changes in IC technology, as well as lead attachment, in order to predict electrical performance, power densities, and specifically cost and first pass yield. This is never turned into a product. It was far too complex, and unfortunately, since it was written over 30 years, there was actually no operating manual. And if you looked at this crosswise, the Excels would all go into errors. So troubleshooting it, if something went wrong, was a little wild. But it did demonstrate, and I've used it hundreds of times to redesign a product for people, especially the question, we took this complex multi-layer and used HDI. How long would it take it? What would it cost us? And what would the performance be? And using this software, I could produce a report for somebody of the simulated prototype that said, well, this is what the HDI board's going to look like. This is what's going to cost. That's why I contend that HDI is basically for electrical performance enhancement, but it's also reduction of cost. And the reduction of cost comes in understanding, how you can miniaturize and shrink the board to get more up per panel, or reduce layers of expensive, non-FR4 materials, things like that, into a new generation to help teach people, how to do it this way from the very beginning. Now, I'm hoping that digital twin analysis modeling that we talk about will help provide the industry with software products that people can buy. Like I said, the tools that I have are not for sale. And when I tried to develop them at Mentor Graphics, we had an actually working prototype on this, but chose not to market because management felt it was too complex. In other words, my team and I could use it, but I had many, many years of experience, we had not figured out how to make it usable for someone with only a year or two out of university with that. So the predictive engineering framework, needs to take the product data management database from history, as well as these metrics we talked about last week, and do a predictive engineering trade-off modules that give you price performance, and then can produce from a CAD program generator the CAD technology file that actually sets up the CAD system to design the board that we have optimized. And it kind of looks like this. So the industry framework provides an architecture of trade-off models and supporting software for various digital twins. And I'm hoping that, eventually, this type of framework is available to people. So not just the physical design, but also the predictive and planning design that is based on real manufacturing feedback data. So the IPC working on this from 2581, the factory 4 goals of data transfer directly to and from the factory is a fundamental part of the IPC CFX in 2581. And you'll hear more about that, fortunately, next week, as we have another author. So, the figure of merit we talked about last week, can create a model when no expert opinion are available. regression coefficients can be used within these models, but the design of experiment coefficient will provide coefficients of linear and nonlinear equations to help provide these models. And remember, we talked about in the very first one, the Engineering Statistics Handbook, which again, if you haven't downloaded this from NIST, I advise you to go ahead and do that, since I have no way of guaranteeing this is going to be available. I've given you the URL. You can't get to this from just going to nist.gov. It's no longer on their menus, but you know, the www.itl.nist.gov/division898/handbook will get you to the actual handbook over there on the left, showing you the 8 chapters and also the tools and aids, which will provide you with the state-of-the-art software statistics and training. Other ones for this is from EWI, Design of Experiments for Engineering Challenges, a good resource that you can download from the internet if you want to know more about design of experiments and its usefulness. Lastly, I want to talk about distance learning. Again, like I said, this is only a 15-minute quick tour of a topic that you can read about in the ebook, but that is not sufficient training. In order to prioritize and training, you know, you need to create for yourself or for your company or for your team a roadmap of which of these skills are most important in your business climate and how you're going to learn the expertise of this, like the courses that I've taken. Fortunately, we have a thing now called distance learning. And like I said, as of 2007, as many as 12 million people are taking online courses from various universities and technical companies. Nearly half are not in the US, even though these courses are taught in English. Today, the estimate is more than 25 million, with 2/3 of learners outside the US. So these are involved with 21,200 college-level programs designed to be completed totally through distance education. Now, the interesting thing is that if you're not signing up to take these courses, your competitors are. And the people competing for your job and your location, most of them are outside the US, taking advantage of the knowledge the US has. And so distance learning started after the Vietnam conflict. The military realized the need for continuing education for soldiers, airmen, and sailors. And today, more than 4.6 million hours of distributed learning takes place in the US military every year, whether on ships, foreign bases, or in barracks. In 1987, the United States Distance Learning Association was formed as a nonprofit organization by J. Taylor Holden from his work done in the Department of Defense in setting up distance learning for the military. And yes, this may be related to me. This is my younger brother. They support research, development, and dissemination of best practices across the pre-kindergarten to 12th year, higher and continuing education, corporate training, military, homeschooling, telemedicine, government training, and others. And this is where the rest of the world is getting their knowledge. They're getting their knowledge from the best that we have to offer through distance learning. So retooling or upscale will require high-tech new skills, as well as help and collaboration from industry and universities. A priority is that distance learning will also lead to a meaningful credential, whether it be a certificate of completion, certification, or degrees. Since 1988, some universities have made great strides in collaborating to develop and provide education and training on the entire industry. So we move from this face-to-face real-time learning model that I grew up with to development of in-person webinar like we have here, in which, in real time, I'm interacting with the audience, to the distance learning, which is personalized, and anytime the instructor is not in real time with the student, the person's learning. And so distance learning is more than just an audio track on a set of PowerPoint slides. And as you go into this again, it was taught to me by my brother, but who utilized this? Well, the non-English speaking countries that use English for the technical people, you can see there is quite large. If you're primarily in English speaking countries like US, the UK, Canada, Australia, New Zealand, South Africa, India, that's great, but it's also used by other ones. The one that I don't have down there, or at the top of the list, is Taiwan. Having lived a number of years with the Taiwanese, I can assure you that Taiwan engineers are using McGraw-Hill handbooks and McGraw-Hill things, the same textbooks that I used at the university. And though they are primarily not an English-speaking country, if you're in engineering, you can read and write English, even if you're not very good at speaking it. So the emerging technologies access resources and provide tools through a number of different things, like you've seen YouTube come along, and provide interaction and the aggregation of information and data. As you can see here, the affordance of emerging technologies, be it blogs, Skype, Wiki, Second Life, Bookmark, image sharing, Facebook video, Google Reader, has expanded. But the online learning environment actually comes about because of a team that it takes: an instructional designer, the graphic article, the content matter expert, usability expert, programmer, social media. My brother, defined me as the content matter expert, and in this case, something about automation and printed circuits. But for an online effective learning course, I'm just one of 5 additional experts used to put together, this thing, because teaching online requires a support team in terms of the instructor, technical support, accessibility, tutoring, administrative support, and learning development. So what came out of this is a thing called the MOOC, which is the massively open online course method of distance learning, in terms of its 2 variants, X mode and C mode, in terms of role the instruction, credits, start and end dates, being self-paced, testing, interaction, and many of these are what we call open content. As I'll show you, starting in the early 2000s through 2007, the Open University technical open education to face-to-face and face-to-face teaching, which still exists in the thing, but the MOOC has developed, especially at corporate training and competency-based education, new models that provides us open education resources for everyone. So some of these I've listed here. Stanford Online is a nonprofit from Stanford University, founded in 2006. The content license is free. It's not for profit. It's free to access and providing institutional credit. And so we'll go through here, Coursera, Khan Academy, you probably all heard of. It's again a free one, and it's free to access. Canvas, Academic Earth, Udacity, P2PU. This is University of New South Wales and University of Canberra from Australia. Again, the content is free. Open Classroom, prescribed by Google, Microsoft, IBM. EDX, institutional, MIT, Harvard, Boston University, UC Berkeley, Kyoto, Queensland, Bombay, Dartmouth. Again, free, not for profit, but they don't provide institutional credit. Nova Ed, again, Stanford, Wharton, Princeton, Comcast, Carnegie, University of Madrid, and then Cosmos, University of California, Berkeley, UCLA, University of Michigan, Oxford, Cadence, and Udemy. So this is just a partial list of providers. They come more and more are actively pursuing this and being involved, that you can then find the courses you need. As a reminder, there's a reading assignment on your own. In other words, we won't be covering Chapter 6, Technical Writing, or Chapter 23, Technology, Awareness and Change, or Chapter 12, Project and Program Management. But there's 24 chapters, and I advise you to read all of them and put them in place in terms of where you may need them. At the front of there's a chart, in my best estimate, as you gain these skills, some of these skills in the chapters are essentially needed for promotion, become engineering manager or chief technical officer, et cetera, et cetera. So this can be a long range program that you're working with. As a bit of benefits, we'd like to introduce that we've added to the program that will be taking place next Wednesday, November 2nd, again, 4 p.m. We have another expert prepared and volunteering his time, and that's Michael Ford, who's the Senior Director of Emerging Industry Strategy at Aegis. He's from the UK, and he'll talk about software-driven automation, real value after removal of smart manufacturing barriers. Michael is clearly one of the experts in this area, and 20 years my junior, but focus on this nonetheless. So in addition to Michael, we'd like to encourage any of you there that have questions or suggestions to send it to me or to Bill. And if you have suggestions of module that should be added and or additional modules that I should teach or someone else should teach, always happy to hear from you, including after next week. Maybe we need to schedule through Bill another 1 hour session in which Michael and I form a panel, or Michael and I and anybody else you can recommend. And as you log in, you can ask the questions and we can discuss this from our point of view in real time. Whatever it is, thank you for your time that you've given me. And I hope to see you again next week where we continue on this program.